Good morning, everybody. Welcome to this breakfast seminar. My name is Dragos Ilie. I'm an assistant professor at PTH, where my research and teaching is mostly in the area of security. This is the agenda for today's talk. Most time that is allocated is going to be me ranting about bugs, specifically bugs that can cause buffer overflows. But towards the end, I will also provide some general information about the PROMIS project, the courses we offer through it, and some hints on how to apply for such courses that meet your interests. So the reason I'm going to talk about bugs today is because for many years ago, I used to be a software developer, and some of my finest memories have to do with the times I was able to implement a new feature and I was seeing it working correctly for the very first time. But also as a software developer, I had to fix bugs, and I had to fix, of course, my own bugs, which is less fun than adding new functionality. I also had to fix other people's bugs, which could be very annoying at times. And I had also to fix bugs that would threaten the security of the product I was working on. And that could make me feel stressed and anxious. So these are my personal motives for talking about bugs, but of course there is a more objective reason, and that's the fact that bugs as a global problem, they cost society quite a lot. So to get some feeling about the cost related to software bugs, I looked into some studies that were done previously, and I've collected 3 of them. So the earliest is from 2002, and it looks at annual cost of software bugs across the United States. And when we're talking about cost of software bugs, it's not only the cost of fixing the bugs, but it also the cost of having businesses stand still, and lawsuits and money paid in damages. And we see here billions and trillions. That's numbers with a lot of zeros. And at least myself sometimes have difficulty getting some perspective. So to get a better feeling about how much they mean, I have an example. The Swedish government expense budget for 2020, it's approximately 110 billion US dollars. So this includes money to maintain roads, to make sure hospitals and universities are running. So if somehow magically we would find a silver bullet that would eradicate all software bugs in the world, then the world economy would have enough money to run 17 countries the size of Sweden. So I think that's a pretty big cost that we have to carry. Of course, there are many root causes for bugs. Due to time constraints, I'm going to focus on a single one, that's complexity. And first of all, I'm going to look at complexity in software products, and I picked 2 of them here. I picked the Linux kernel and the Windows operating system. And what you see on the y-axis, it's a million lines of code in the source code for these products. And this is not meant to be comparison, it can be a fair comparison, because the Windows product contains much more than the Windows kernels. It also contains free applications that come with Windows for free. What I want to sort of show in this picture is that the size of software products increases over time. Although we see a drop from Vista to Windows 7, the reason for that, it's most likely code refactoring that occurred in Vista, because when Vista appeared, a lot of customers were disappointed with the quality in that product. I don't have numbers for Windows 8 or Windows 10, and if you do and want to share them, I'd be happy to update this graph, but I'm pretty sure that the blue curve would still go up. Most, or I would say all software products I worked with or I encountered through my lifetime, they have over the years just gone up in size. And if you have any examples of products that have been shrinking, then I'd be happy to know, because that would make a nice counterexample for my students. So what we have is software products increase in size. Developers like me create bugs, and hopefully many of these bugs are caught in testing. But unfortunately, we do know that others escape into the wild. So, of course, one would like to know, okay, so approximately how many bugs are there? And that's a very difficult question to ask. But we can try to answer it in the context of these two software products. And to do that, I'm going to use a very old statistic that comes from the Microsoft development team in the 90s. They claimed that they had approximately 0.5 errors per 1,000 lines of code, which was pretty good at the time. If we want, we can, it's a guessing game, so we can do it. We can assume a tenfold improvement over 25 years. Personally, I don't think that's very likely, but that would mean we have 0.05 bugs per 1,000 lines of code. So if I extrapolate the numbers from the graph I've shown you in the previous slide, this means that the Linux kernel 4.0 shipped with 750 dormant bugs, and Windows 7 had almost 2,000 dormant bugs when it was released. Of course, it's a guessing game, so don't take these numbers too seriously, but I wanted to look for a hard fact, and I went to see the latest Linux kernel release. That's from May this year, and in the change logs, there were 105 listed bug fixes. So we do know that we have a lot of dormant bugs out there just waiting to be exploited. Now, for this talk, I'm going to focus on a specific type of bugs. That's input parsing bugs. And the reason to do so is actually quite eloquently put by the editor of the Usenix login magazine, Rick Farrow. The text in blue there, it's my own, just to increase clarity. So Rick wrote, there is a programming issue, input parsing, that is a single cause of most exploits. Fixing this would do more to improve security of our computers, cars, smartphones, and devices than would any other change. So I think he expresses quite well, and this is the reason I'm looking at these bugs during this talk. So this is sort of a crash course into what the buffer overflow is. So I tried to illustrate that using some C pseudocode, which is written in blue. So the first line here, basically what it does, it reserves two variables. These are two arrays, A and B. B has a size of 2 bytes, A has a size of 8 bytes. And then for the first byte in B, we allocate value 0, and for the second byte, we allocate value 3. And then the third instruction here, what it does, it's basically prompts the user on the command line to enter some text, which is then copied into variable A. And in C, strings don't have a length indicator. We only have a indicator for when the strings is ending, and that's the value 0. It's because that one never appears in printed text. So the way scanf does, it is basically iterates through the bytes through the characters that are entered by the user, and when it encounters a null character, then it stops. And in this case, what we can see is that the user entered the word excessive, the largest part of the word fitted into the array A, but the reminder spilled over to the variable B and overwrote its contents. And of course, the question is, what would an adversary be able to do by overwriting nearby variables? And that's probably, I always like to do some sort of practical things when I do lectures, so I prepare something here. So I hope everybody can see my virtual machine. And here I have a very simple program. It's written in C. And even if you haven't encountered C before or C programming, don't worry, because it's a simple program and I'll walk you through. So this program is compiled. When you start it, then you have to enter on the command line a password. And that password is compared to a number of predefined passwords available in this program. So the program starts in the function main here, and it receives the password inside these arguments. And the first if statement...
Sorry, Dragos, need to help. We don't see the virtual engine.
You don't see the virtual machine?
Oh, we see only demo time. Sorry.
Aha, okay, let me see if I can fix that. Thank you for letting me know. Let me use this, that.
Is this better now?
Yeah. Yes.
Okay, so sorry about that. All right, so this is a program. Program starts in function main, and it receives the password from the command line in one of these arguments. And the first if statement here, it just checks that the minimum number of arguments has been entered. That's the password argument. So it's not so important. The second one will take the memory address where the password is stored and pass it to a function called checkAuth, that is check authentication. This function will compare the entered password to two predefined passwords that you see above, boss and manager, and it will return true if we find it's a match, and in C, true is any value other than 0, or else it will return false, which is value 0. So depending on what's returned, you'll see either access granted or access denied. So I'm going to sort of try to demonstrate this. So this is my program, overflow 1. I have many overflows, but this is the first one that I'm showing you. So I enter boss, which is one of the predefined passwords. Yeah, seems to work. I enter manager. Yep, that works too. And if I try Dragos, then I get access denied. And now what I'm going to do is I'm going to try to create a buffer overflow. And the reason this buffer overflow exists, it's because of this instruction in the checkAuth function, string copy. So what happens, checkAuth receives the address of the password in memory. Then it reserves a buffer that has a size of 200 bytes. And then it has an authentication flag that by default is set to 0, which means false. So this variable is what's returned to the main function. And then the string copy function, what it does, it copies the contents from the memory indicated by password into the password buffer defined above. And as I said before, in C, the way you copy strings is that you iterate over the characters until you hit the 0-valued character, and then you stop. So the question here is, what happens if the adversary would pass in a string that's longer than 200 characters? I'm too lazy to actually write 200 characters, so I actually prepared a Python script to do it for me, and this is what the Python script does. And let's see. Here is my program, overflow 1. So I'm going to just pass in the output from this tiny Python script, this one-liner. And voila, it says access granted. So basically what happened here is that when I overwritten the password buffer, then 200 characters, that's how much it can be stored. The remaining A character went and overwritten the auth flag, making it from false to true. And this is what's being returned to the program. And this is a very trivial example, but the reason I'm showing it is because when you do write C or C++ programs and you do a lot of string copying, and people always forget to or frequently forget to check the size of the things that are being copied around. And this can be used by adversary to bypass different checks that are being used in the program. All right, so I'm going to return now to my PowerPoint presentation. Let's see. Okay, everybody sees this? I hope so. Otherwise, please tell me. All right, so as a second example, I'm going to show you another problematic way of doing parsing, and that's when you do lenient syntax control. So normally when you read data from the outside world into a program, then you expect it that it's formatted in some way, and then you try to sort of implement a parser that understands that format and reads the data correctly. But in some cases, the parsers, they are very forgiving. So for example, you probably know that in HTML, you can even leave out some tags, but the page will still display correctly. However, this can be the cause of a problem, as I will show you in this next example. This is a bug that existed in iOS from iOS 11. It was just fixed for a few weeks ago. And there was a bug that was just revealed by its author. So what happens is in iOS, you have applications. These applications, they have something called entitlements. And this basically, the application in iOS, they need to run in a sandbox. And the entitlements are, well, you can think of it as access rights. They allow you to punch holes through the sandbox in order to do different things. However, in order to make sure that people don't break the security model of iOS, there is always a provisioning profile that's installed on your phone by Apple. And all these entitlements, they checked against a provisioning profile. And the entitlements, they are being described using XML. And you can see a little bit how they look on the left side of my screen. And the sort of the faulty line, the one that permits these bugs to happen, is marked in red. So that's the first line. And that resembles a XML comment, but as you can see, it has an extra dash too much. And the problem is, crazy as it seems, iOS actually makes use of 4 different XML parsers in order to handle these entitlements. And these are actually quite lenient towards how they process the entitlements file, or this is what's passed to them. And the problem is the first one, which is in user space, then basically when it looks at the first line marked in red, thinks that this is a comment, this is the beginning of a comment, and then treats the reminder of what you see here up to this point as the contents of the comment, and basically doesn't parse it, but passes it to the kernel. And the kernel also does some sort of a lenient parsing. It recognizes this as a erroneous XML comment, but then just skips over and keeps going until it reaches the second line in red, which basically tells it, please run this application outside the sandbox, which means the application can talk to other applications. It can access user data and devices on the iPhone. So this shows, again, the dangers of doing sort of lenient input parsing. Now, why is input parsing difficult? Well, previous experience has shown that on the average, the programmer is bad at parsing complex input. And in fact, Matthew Garrett, a security expert, he wrote, as a species, we are pretty bad at writing code. We are even worse at writing codes that deals with data. And we are astonishingly bad at writing codes that deals with arbitrary user-provided data. Of course, this doesn't quite explain why it's so difficult to parse input data. So I'm going to try to sort of give you a feeling for that. So I'm going to look at complexity again, and this way I'm going to look at it through state machines. So I'm going to show you a state diagram. And for those of you who are familiar with networking, this is a state machine for TCP connection. So it basically tells you the different phases through which a TCP connection goes, whether it's waiting for some connection to be established, whether it's trying to actively establish a connection, or it's sort of a sending or receiving data. So what we see here, this is a state diagram. The boxes represent the states in which this state machine can be, and then the lines, they are just transition between states. So this is pretty high-level state machine that explains how programs should behave. To the right, I have a different example, and this is control flow graph from IDA Pro Disassemble. And what you see here is basically the assembly code for the ls command in macOS Catalina. And again, this is a state diagram, and the states here are boxes, basic blocks as they're called, which contain assembly instructions. And then this, the lines between them represent transition between the different states. So when you program, then as a programmer, you build some sort of mental representation of this type of state machine. And you do it for various reasons: to understand the misbehavior of the program, to identify error states and unwanted transitions, or to find the best place to make modifications, or to add features, and to anticipate any side effects that changes may bring. The problem is most practical state machines that we deal with when we do programming, they're too large to fit in our mind. So we only have parts of them, which means the model that we have, it's incomplete. So incomplete models will make us sort of miss certain possible transitions that can occur which means that when the process is running specific data, then the process can go beyond the intention of the programmer. Now, what we need to understand here, what we need to keep in mind is that transitions, they occur due to state changes. These occur either internally as a result of performed computations, or most frequently they're driven externally as input data that comes to the program. So what we need to understand is that state transitions, they are controlled by data. And in fact, Taylor Hornby, an expert in security, he had this statement: the illusion that your program is manipulating its data, it's powerful, but it is an illusion. It is the data that's controlling your program. So how does that help? Well, I'm going to again try to show you a demo. Hopefully this time it will go much smoother than the previous time. I'm going to return to my virtual machine. All right, so this is the same program. Before I just was able to skip a check. What I'm going to show you now is, and what is important to realize is what you see here is really the contents of the program. There is nothing else hidden. What I'm going to do is I'm going to provide some data to this program, and parts of this data, it's going to alter the state of the program so that it will actually read in the remaining part of the string that I provide and execute it, because what I do provide to it, it's a computer program. And the effect of that will be that of a remote shell. So let me demonstrate first. I have another window here. Let's see. This is the IP address of this virtual machine. And I'm going to use Netcat. Netcat just connects to an IP address and port number, and it basically acts like a pipe. It sends and receives data. And there is nothing listening on that for now. And I wish I could do this with a one-liner, but unfortunately I had to build a C program that creates the actual string for me that I need to pass into the vulnerable program. So what exploit does, it constructs a string, and then it calls overflow1, the program I've shown you before, and passes a string it's sort of created. So this is how it looks. So this is the program that's being called, overflow1, that's a vulnerable program, and this is a string that's passed to it. What the string does, it alters the state of the overflow1 program and then makes it execute another computer program that's inside the string. So now if I go back, ta-da, I am actually able to connect to my remote shell. And what can I do here? Well, I can list files. I can even create files. So let's see. I can actually make this executable. And just so you see that this actually took effect. Here is the file, and here are the contents. So what this means is that as an adversary, if I'm able to punch such a hole through your program from remote, it means I can create executable files, and that means I can copy programs onto in your computer, and I can execute them. And if the vulnerable program is owned by root, I basically own your machine. So I'm going to return now to the presentation. All right, so I need to make a disclaimer. In order to make this running, I did have to turn off some of the operating system and compiler defenses, because the thing that I've shown you, it's quite old. But the reason I show it is because it allows me to show how you can actually do a buffer overflow or stack smashing with a very, very simple program. I can bypass all these defenses, but then the program that I would show you would be much more complicated. Now, the question is, well, when you do this sort of thing, what sort of capabilities can you get if you're able to run this sort of exploit? And again, a smart developer, he wrote, Any sufficiently complex input format is indistinguishable from bytecode. The code receiving it is indistinguishable from a virtual machine. This means that basically the overflow one program, when I change its state, I basically made it into a rather dumb virtual machine, but that's perfectly capable to run programs, arbitrary programs that I send to it. So this means that we have lots of bugs out there. Some of them can be actually exploited this way, and that those bugs we don't know about, they're zero-day, and they make dangerous zero-day vulnerabilities. And those are in very high demand. So let's see. And if you're interested about how much the demand is, well, there is a company called Zerodium, and their business model is that they pay bounties for bugs that can be exploited, and they pay the bounties to developers or to researchers, and then they sell these exploits to government agencies or to governments that are interested in this stuff. And you can see the different pricing. To the left is for desktops and servers. To the right is for mobile applications. And quite interesting here, for mobile applications, is code signing bypass for iOS and Android. And that's exactly the type of bug I've shown you in the iOS operating system. So the guy who had the bug, who discovers the bug, could have obtained a bounty up to $100,000. Well, I hope this sounds interesting. And if it does, you should know we have a program. Currently, this program is targeting active industrials studying and working at the same time. The program will provide university-grade courses, and it will extend current competence in a single area in security. We are open for case-based pedagogy, which means that if you want and you are allowed by your boss, you can bring your own problems to our courses and try to work them in the context of the course. We can provide online collaborative didactics, and we have distance capability, including labs and tools. And the courses under development, we do that with input from companies in order to keep the courses relevant and at the right level. And if you and your company want to be part of this, then please, you can contact Anna, and her email address is there. We currently offer 3 courses. The first one is software security. That's my course, and it will build on this sort of topics that I presented during this presentation. You will gain the ability to understand how attackers exploit risky programming practices, the ability to detect risky programming practices, and you'll be able basically to reason about efficiency and limitation in existing software security mechanisms. The second course, it's quite related. It's a web security course, web system security course, and it looks specifically at web applications. So it looks at things like cross-site scripting, how you can exploit things using, for instance, JavaScript and SQL. And this course, the responsible person for this course is Anders Carlson, so if you need more details, then please contact him. And then the third course is called Security in Software Intensive Products and Service Development. And this takes a more architectural approach. It looks at technology, operational aspects, and engineering aspects of security. So the course focus is on engineering security. And the course responsible for this, the responsible person for this course, it's Tony Gorshek. Please contact him if you have questions about the course contents. Please spread information about our courses to your company. The PROMIS courses require at least 120 credits, of which at least 90 credits are in a technical area. And they also require a minimum of 2 years professional experience within an area related to software-intensive products. And keep in mind that even if you don't have the formal academic merits, you might be qualified to the course through validation, something we call real competence. And there are 4 simple steps to apply for the course. Create a user account at antagning.se or universityadmission.se. Search for the PROMIS course that you're interested in. Fill in and send your application. Upload the required documents, that would be the employer certificates that you have these 2 years of professional experience. And reply to any offers of admission. And if you have any questions about courses, contact the course responsible person. Questions about applying and validation should go to Anna. And For more information, please visit our website at promisedu.se, where you'll find updated information about courses, application, and template for the employer's certificate. Thank you very much for using this morning to listen to me. I hope it was interesting, and I hope to see you in our courses.